Hi folks, and welcome to our Chapter 9 narrated lecture slides, Acids and Bases. So today we will be going over some of the basics for defining acids and bases, where we use them, how we solve for pH, and also some nomenclature just to review. So we technically have two different definitions of acids and bases. The first comes from the concept of the Arrhenius definition of acids and bases, where an Arrhenius acid would be any substance that provides a hydrogen plus cation or hydronium ion when dissolved in water, and that an Arrhenius base would provide a hydroxide or an OH anion. The other definition of acids comes from the Bronsted-Lowry definition, where we're looking at it in terms of donation or acceptance of the hydronium ion. So a Bronsted acid would be the substance containing a hydrogen that would then be donated, and a Bronsted base would be any substance capable of accepting that donated hydrogen. Really, one of the big ones where this comes into play would be things like water, where water can behave as both the acid and the base, depending on which way, which water molecule is giving up the hydrogen and which water molecule is accepting it. So oftentimes when we are doing these types of reactions, we want to be able to identify on the reactant side which one is going to be the hydrogen donor, on the reactant side which one would be the acceptor, and then on the product side what the resulting materials would look like after that donation and acception has occurred. When we have this donation and acception, we end up with what we call conjugate acid-base pairs, and this would be essentially something where we look to the reaction side and we follow it through to see what did it become as a product. And if we were in equilibrium in the reverse reaction, for example, if we had an acid, something that donated a proton, the product of that material, that substance, would be a base. If we were to go in the reverse direction, it would be the thing to accept a proton. And so we would call this a conjugate acid base pair. It's simply a way of talking about the conjugate of whatever we originally had in our reaction. So here, for example, we have an acid, which would be our proton donor. And this is the resulting product of that donation of the hydrogen. And we can see if this reaction was going in the reverse direction, that the base, this would be now a base, as it would be accepting a proton to become this again. As always, I'll leave these up for you to utilize as a kind of practice for yourself. We've already done plenty of binary acids. You've seen them earlier. This is just kind of a refresher since we're in the acid and base chapter. When we're naming our binary acids, again, remember things like we're going to add the prefix hydro, and then we're going to add the suffix where we're going to cut off the "ide" portion of the name and add "ic" to it. So we would have something like hydroiodic acid. When we have polyatomic ions, this is that ate-ic, ite-us. Basically, if our polyatomic ion ends in ate, the acid will end in ic. If the polyatomic ion ends in ite, the acid would end in us. So we talked briefly about this in an earlier slide, but the concept of the self-ionization of water. Water is kind of an interesting and unique species in that pure water contains only H2O molecules, but we will actually also have small amounts of H3O plus and OH minus ions in there, and that's because of this self-auto-ionization of water, where one water molecule will act as the base and one water molecule will act as the acid. So it's a pretty unique situation where you have this occur, but because it's going to occur within just pure water, um, we're going to have equal concentrations or equal amounts of the H3O plus and the OH minus. And this is how we end up with things where, when we look at it, we end up with, in pure water, a concentration of 1.0 times 10 to the negative 7 molar for each of those ions, the H3O plus and the OH minus. And since this is in equilibrium, right, it's going to help be the basis of kind of like all solutions when we're dealing with their pHs, right? So an acidic solution, we're going to have a concentration of H3O plus that is greater than the concentration of OH minus, right? Acidic solutions we know are going to have low pHs, anything under 7. A basic solution would have a greater OH minus concentration than the H3O plus, and this tends to lend higher pHs, 7 and above for basic. So basically what we're looking at when we talk about the concept of pH, we're looking at the negative logarithm of the concentration of H3O plus. Sometimes we abbreviate it as just H plus, but we're really thinking H3O plus because in water, any aqueous solution, that hydrogen cation is going to combine with the water, and this is a more stable kind of species. So what we can see here, right, is these brackets indicate that we're talking about the concentration of the H plus, and so we can go from pH to the concentration of the H plus, or we can go from concentration of H plus to the pH, depending on how we manipulate the log and the exponent. So very quickly and simply, if we are to calculate the pH of a solution, based off of a given hydrogen cation, hydronium ion concentration, we would use the negative log of the concentration to give us the pH of that solution. We can also do pOH, so or we could look at utilizing the OH concentration as a way to find the H plus concentration to do a pH. And when we do that, we're going to have to first go through and identify what the OH minus concentration is. If we are told, for example, the pH is 4, we would be able to use the exponent of the pH times OH minus, because we know that H plus times OH minus is going to be 10 to the negative 14. So we can work backwards to figure out what our OH minus concentration is. Again, make sure you're comfortable utilizing your calculator when solving these. Please make sure you're using a calculator, not your computer, not a calculator simulator or anything on a computer. You want to be quick and precise as you're going through and calculating, so that especially on tests and quizzes, you're able to find the proper buttons and do your calculations quickly and efficiently. Moving on from naming acids and kind of dealing with their pHs, we want to talk about relative strengths of acids and bases. And what that term really means. So a lot of times the concept of a strong acid or a strong base is mistakenly confused with how dangerous that strong acid or strong base might be. But that's not necessarily true, and that's not necessarily the case of was defining something as a strong acid or a strong base or a weak acid or a weak base. It has nothing to do with how caustic it is. It's how those acids and bases behave in the presence of water, in the presence of being in a solution. So we say that strong acids and bases dissociate 100%. They completely ionize when they are in water. So this would be any sort of aqueous solution where when we see it and we see that it is an acid or a base that is in an aqueous solution, that we should understand that that's really the summation of the two cations, or the two ions present, the cation and the anion, that they fully dissociate, they fully break apart. Weak acids and weak bases only moderately or minorly dissociate. Very few of the um, atoms in the solution are going to be individual cations or anions. Oftentimes, in a weak acid or a weak base, the full molecule is still present. So we have more dissolving going on than dissociation for weak acids and weak bases. Here's just an example to kind of go through the different kinds of acids we can have. We have monoprotic, diprotic, and triprotic. And this is really just dependent on that acidic hydrogen, or which hydrogens are the ones that are going to be given away. Some molecules only have one obvious hydrogen that would be given away, while others can have two or even up to three. And so when we say monoprotic, diprotic, triprotic, we're talking about the protons, the hydrogens that will be given up. We talk about buffers in our discussion section for this week. But again, we want to be comfortable with the concept of buffers, their ability to resist change in pH, and that's often because we have a system set up where if the acidic content of the system were to increase, then more base would be produced, or that equilibrium could shift based on Le Chatelier principles and cause more acid to be produced if we were in a higher alkaline situation. So a lot of buffers, right, in terms of what we are familiar with, typically are made up of a weak acid and the salt of that acid. Physiologically, buffers are crucial to homeostasis and the ability of whatever organism uh, those buffers exist in to resist changes in pH, often due to ingesting of foods or something along those lines, or any other sort of outside influence on the environment. This concludes the short little foundational narrated slides for Chapter 9.